In number 24, they give us the function g of x equals the cube root of x, and they give us the closed interval -1 to 1, and they want us to find the absolute extrema. So I'm going to start by finding the derivative, and I'm going to keep in mind that the cube root of x is really x to the 1/3. So the derivative is going to be 1/3 x to the -2/3, which is the same as 1 over 3x to the +2/3. Okay, so I've got to ask two questions. Where is the first derivative equal to 0? And where is the first derivative undefined? Okay, so if I say 1 over 3x to the 2/3 equals 0, which I'll make 0 over 1, and I cross multiply, I end up getting 0 equals 1. And that doesn't make any sense. So my conclusion here is that there are no critical numbers because of this part of the problem. Now when I look where is the first derivative undefined, I say, well, for the first time in all the examples that I've done on the computer here, we have a denominator that has a variable in it. And if that variable is 0, we get an undefined situation. So we know that x is going to make it undefined. When x is 0, it'll make the derivative undefined. So this is our critical number. Okay, so when we make our chart, we're going to have our left endpoint, we'll have our critical number, and we'll have our right endpoint. Our left endpoint is -1, our critical number was 0, and our right endpoint is 1. This is x, and this is f of x. Okay, so if I plug in -1 to the original, the cube root of -1 is -1, the cube root of 0 is 0, and the cube root of 1 is 1. So the lowest value is going to be -1, so we're going to have a minimum at -1, -1, and we're going to have a maximum at 1, 1. So in this case, the absolute extrema happen at the endpoints of that closed interval. Let's confirm. Now, I know that a cube root function looks like a sideways wiggle or a swiggle, but we'll take a look on the calculator just to be completely sure and on the same page. So I'm going to come over here. Y equals math for x. This is the cube root function. I'll make this bold. I'll go to my window. I'm going to go from -1 to 1. And I'm looking at my lows and my highs, and they're -1 to 1 also, so maybe I'll just say -2 to 2. Here we go. Here graphs my sideways wiggle. And the lowest point is over here, which is -1, or 1 to the left and 1 down, -1, -1. My highest point is here, 1 to the right, 1 up, 1, 1. Again, confirming graphically our solution that we got manually doing the calculus. Number 26, they ask us to find the absolute extrema of the function y equals 3 minus the absolute value of t minus 3 on the closed interval from -1 to 5. So this is an absolute value function, and I know that to find the derivative, I'm going to need to express this as a piecewise function, which means I first have to, for me anyway, draw the graph of this, just a real rough sketch so I can get a sense of what's going on here. So to start, I'm just going to rearrange the order a little bit, and I'm going to call this the opposite of the absolute value of t minus 3 plus 3. When it's written in this way, it's just, I don't know, I can understand what's going on a little bit better. So I'm going to draw some axes right here, and this tells me it's going to be 3 to the right, 3 up, and then turned upside down. Okay, so I'm going to label some significant points on here. This point right here at the top is 3, 3. And I also know that if I plug in 0, the output of that's going to be 0. So it's 0, 0 is also a point. That's going to be this guy here. And this point over here, just using sort of the properties of symmetry and knowing that these v's are symmetric, this is going to be 6, 0. So now what I can do is redefine this as a piecewise function. So y is going to equal two pieces. The first piece is going to have a positive slope of 1 and a y-intercept of 0. So that's done. The second piece has a slope that's -1, And if you continue up, take a guess as to where this is going to cross. You could do the algebra, but it's going to cross at 6. So that means the y-intercept is 6. And this first piece exists for all x's that are less than or equal to 3. And the second piece exists for all x's that are greater than 3. And when you take a derivative of a piecewise function, you take a derivative of both of the pieces, or all of the pieces involved. So the derivative of x is 1. The derivative of negative x plus 6 is negative 1. There's one interesting thing that has to be stressed here. When we write the restrictions, the derivative is defined for x less than 3 and also for x greater than 3, but it's actually not defined for 3 itself. And if we look at the graph, we see that there's a sharp turn or a cusp there. So that point 3 has to be omitted. It's not part of the derivative. It's not defined there. So when we go to our two questions, where is the first derivative equal to 0? And where is the first derivative undefined? The first thing we can say is that it's undefined when x equals 3 because of this cusp. So that's going to be one of our critical numbers. Now, where's the first derivative 0? If we look at our first derivative, you could say, okay, well, when does 1 equal 0? That never happens. When does negative 1 equal 0? That never happens either. So this doesn't contribute anything to our list of critical numbers, and consequently, this is our only number that is critical. So let's see. We have our left endpoint. We have our critical number. We have our right endpoint. And those are negative 1, 3, and 5. And we'll kind of summarize this in a little grid. This is x. This is f of x. You could plug this in and do it manually. You could use your calculator, whatever you feel more comfortable with. So if I plug in negative 1, the output is negative 1. If I plug in 3, the output is 3. And if we plug in 5, the output is also 1. So the lowest value is negative 1, which means our minimum is at negative 1, negative 1. Our highest value is at 3, which means our maximum is at 3, 3. Okay? Now, if we do this on the calculator, it's going to look a lot like what I've drawn here in blue. However, the blue is the entire graph, whereas we're supposed to be looking at it only on a very specific interval. So I'll just take 2 seconds and do this. So y equals 3 minus the absolute value of x minus 3. Let's see, let's make that thicker. Okay, let's go to our window and make the x min negative 1. Let's make the x max 5. And I know I'm dealing with numbers that aren't so big for my y's. I'm going from negative 1 to 3, so maybe negative 5 to 5. And we're gonna see a portion of this v. You might even imagine what you're gonna see before I even press graph. Okay, so on this closed interval, the lowest point is over here to the left. We got negative 1 doing the calculus, and sure enough, that's justified here in the graph. Our highest point is the changing point where it changes from going up the hill to down the hill, and that's 1, 2, 3 to the right and 1, 2, 3 up. So once again, we're just confirming and sort of reestablishing the connection between doing the calculus and the visual representation of the answer.